Greetings, math friends. I watched this video on YouTube, and it got me thinking about a variety of things. Some of the discussion in the comment section were about the types of measurements, whether we could convert the chart that he was talking about into the metric system, how or what formula was used to develop the numbers that were in the chart. Having tables in books is a well-established process in academics and in trade. At this point in history, though, some of that has been lost. A while back, I had done a short video discussing this book, which is a table of mathematical information that's published by CRC. This is the student edition, the 17th edition. The video seemed to be pretty popular among people. This particular edition is from 1969. They are wonderful references that have a variety of different mathematical information in it, and it includes calculus. Not all tables are quite like this, but these are nice desk references that you might have had. In this case, this is the student edition, but you, even not a student, may have one of these sitting on your desk if you are in a specific industry which would reference these and you may have forgotten them. We had to think that at the time that this book was being used, we did not have the internet to reference. So you needed another way to reference these values without deriving them yourself. Perhaps you didn't have your old textbooks handy. Maybe a colleague was out of reach, or they couldn't quite remember the formula either. So books like this were valuable. When I was in school, and generations before me, these ideas were not foreign to us. I have a book here from 1979, and in the back of this textbook, you will see that it has a table of values here. This particular table of values is a table of squares and square roots. So again, not reaching for a computer to access the internet or a pocket calculator, you looked in the back of your book for values. Now, some of you that are keen in thinking right now, you might think, well, what happens if the value you're looking for isn't in the table? We were actually taught how to take table values and interpolate between the values given if the number we were looking for was between table values. So that was a skill we had to learn. And I believe I was learning that in possibly 3rd grade. As we move on towards the focus of the video in using mathematics in a shop class, we see this book, The Use of Handbook, Tables and Formulas. So this isn't a book of tables, it's a book telling you how to use the tables, and this is based on the machinery's handbook. So this is the idea you're training people in a machine shop how to use the books that you have to help them with the mathematics involved in a machine shop. So some of these are just basic calculation ideas that you have. So perhaps you're finding the area of a circle. We have some chord measurement here, it looks like. So this particular diagram is finding the length of a hole in the floor for a flywheel. So the chord where that flywheel needs to be level with the floor is what we're looking at here. This textbook is from 1954. And the publishers connected with this are the Industrial Press and Machinery Publishing Company Limited. Industrial Press is from New York, and the Machinery Publishing Company Limited is from England. So this was on both sides of the Atlantic. Another book that I have along these lines of books of table values, this is MacMillan's Logarithmic and Trigonometric Tables. So this is a book of tables, so values that you might need to compute. There's a interesting historical piece in here as well, being that this is predating the age of pocket calculators and the internet. We actually have a brief discussion of the use of your slide rule. So before you had your pocket calculator, you probably had one of these if you made specific types of calculations. If you were in your scientific or engineering or mathematical type of work or academics, you would have a slide rule. The middle of this does slide out, and there are values on the top and bottom and middle bar in this, and then this is kind of your viewfinder. It kind of magnifies there in the middle, and it slides to hone in and look at the particular values that you need to see on the slide rule. So this is predating your pocket calculators. They made cheaper, kind of more disposable versions of these that could be given to people in specific jobs, where you could take them to the job site, and if they get tore up, it wasn't as big of a loss of money as if you had a fancier one that you kept in the shop where you were working in a more controlled environment and didn't have like concrete pouring over them or some such thing. So let's bring this back to the video. In this video, we have someone doing a woodshop project, and they have a book that has a table of values in it, and it's specifically for circle diameters measured in an inch. So first of all, the inch is somewhat arbitrary. If you would said that the circle diameter was measured in 1 centimeter, the formulas don't care. And we'll get into how those formulas work in a bit. But the discussion in the comment section of what if you needed metric, it doesn't matter. Relabel the chart as centimeter instead of inch, it will work just fine for you. You could have labeled that in any unit measurement, it doesn't matter. You could call it a verst. You could call it a dogtail. That is somewhat arbitrary, but it would have referenced probably the expectation of the shop that was using it. If this was a certain period in US history, you would have been using a conventional measurement, so an inch would make sense. If this had been developed for use in Europe, perhaps a centimeter would have made sense, and you could just change that label when you published that table in that book in that region of the world. Doesn't matter. So a question I want to talk about is, where does this chart that was in the book come from? I want to recreate that. So I want to talk about the math behind what we need to know to build that. And this is geometry. So that is right in the field of mathematics that I love to work in, is plane geometry, also known as Euclidean geometry. I also, as an auxiliary skill, being that I'm a mathematician, I know some coding. So I wanted to be able to generate tables by just inputting some values and having a program generate these tables so that I could use them, display them, share them. So that's something else that I want to talk about is now that we have the computer technology, how much faster we can generate these tables. In years past, if you said that it took 20 years to build a logarithm table, one person doing a logarithm table out to, say, 9 decimal places of accuracy, that probably, as scary as that sounds, to work 20 years on one thing, may potentially be accurate. If you don't have a field of people working on this project, you're doing it by yourself, and you don't have a computer, you don't have a calculator, you don't have a slide rule, it may take a while. With the instantaneous process we have in computing nowadays, we can build these tables in seconds. So we are in a gifted period of history to have all of these opportunities. We need to keep in mind we need to use these well to assist us and not hobble us. So let's get into the math. I saw in the comment sections a lot of people are using sine in their discussions to discuss this, and we could do that. There's a couple of ways to do that, but my mind immediately goes to cosine versus sine, even though I am a big fan of sine. But let's look at a circle. We're starting with the idea that we need to know the diameter of that circle. But we want to have a sector defined. We want the intersection of the central angle with the circumference of the circle. If we notice in this diagram that the central angle, each ray of that from the center of the circle to the circumference of the circle, is merely a radii of the circle. Knowing that we have the central angle and we have these congruent radii, and we need this chord which creates a triangle inside the sector, my mind immediately goes to the law of cosines. And because this is essentially an isosceles triangle, it actually makes the calculations easier, which when I wrote the code to generate my tables, I did simplify that formula, so it looks a little different in the code, but it is the same thing. Going back to my standard mathematical tables book, looking in the trigonometry section, which was written by Dr. Howard Eves, one thing that was fascinating to me to realize was this book has trigonometric functions that aren't commonly taught anymore, so we've lost some things to history. One of them is the versine, which I believe used to be used in navigation. If we flip over to page 219 in here, we see the law of cosines listed out in its 3 forms, which is interesting. This book is somewhat for people with a background in mathematics, and yet it still lists out the 3 forms of the law of cosines. We're going to use this form here. Some of you might realize that if we look at the left-hand portion of this, it looks like the Pythagorean theorem. That is no accident. If your angle C is 90 degrees, this is going to collapse to be exactly the Pythagorean theorem. So this is actually the better form because this works for any triangle in the plane, not just a right triangle. The A value and the B value are actually going to be the same because we have an isosceles triangle. So this can be rewritten as 2 times A squared. And over here, A and B again are the same value. So this can be rewritten as 2 times A squared. And that's how I simplified my code. Makes it just a little easier. Not much, I understand, but it made for cleaner code, and I liked being able to put that variant in there. Addressing the debate on whether we use a conventional measure, a metric measure, or some made-up measurement, if we look at this formula, the only thing that requires us to have a specific unit of measurement is going to be the angle measure here, and that is somewhat arbitrary as well. In a shop, we're going to assume that we're going to continue using degree measurements, so we are going to do this calculation with angle C being degrees, but it could have been radians or gradients, or you can make up your own measurement and use that as well, making sure that you adjust the function accordingly. But we know how this works. It's well defined with degrees and radians. And we have calculators for that at this point. And going into writing code, we have ways to declare whether we're using radians or degrees. As for C, A, and B, there is no restriction on the unit of measurement that we use on that. So you could have used miles. You could have used kilometers. It doesn't matter. So when we do this calculation, we're going to label it at the end and declare what we have used as our measurement, and that's the way it's going to work. The next person that comes along can redo this calculation in any of their favorite length of measurement. A quick diagram of our triangle. Our arc of our circle is going to be out here. This intersection between the circumference and the central angle is defining where we're putting this chord. This is the center of the circle. We have this angle C is that central angle. So we're trying to solve for this arc here, which is going to be declared as side C. That's a lowercase c. This is an uppercase C. That is just the tradition that we use. That's somewhat arbitrary as well. We're using a Latin alphabet here. If you're not natively using a Latin alphabet, maybe you don't want to use these symbols either. It annoys me that we teach students in so many places that the Pythagorean theorem is a squared plus b squared equals c squared, which is cute if you know that the first three letters of the Latin alphabet are ABC. However, that doesn't really tell you about the properties of your triangle. I feel it would be better to teach that the altitude squared plus the base squared is equal to the hypotenuse squared, and perhaps use the letter H here instead. This value is known because it is half the diameter that's a given. This is the radius of a circle, so these are congruent. If you're given a diameter, then half of that is equal to the radius, which we've declared is A here. Simple calculation. We plug it in. If you're doing this by hand, a caution to the person computing, we have to be very strict about order of operations here. You can square and then add here. You can multiply this out, but this is a subtraction between here. Do not include your 2 subtracted from this sum because it's part of this product. So product, 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 add, subtract, order of operations that have to be followed. I see many times students will calculate the first few values going from left to right and then subtract the 2 out of this sum of products and then try to multiply that in, and now you violated the fact that you were supposed to multiply the 2 by this, so you can't subtract the 2 from this first. Let's do an example with some specific numbers. To find your central angle, you need to know how many sides to the regular polygon that you're looking for. Think about if this is a machine shop and you have to drill bolt holes. So think the hub of your wheel. Perhaps you have a 5-bolt pattern. You need to have those bolts evenly spaced. So really, in this process, you need a regular pentagon to get that bolt pattern, and then the vertices of the pentagon are where your bolts go. Working with degrees, 360 degrees is the entire circle, so you're going to, in here that we're dividing by is the number of bolts that we need to drill for. In this case, it's 5. So 360 divided by 5 is going to be 72. And let's say that we need a 2-inch space between the center hub and the actual bolt hole. So in this case, our diameter is going to be 4 inches because we need this spacing between the center hub and the bolt to be 2 inches. So if you were given 4 as your diameter, you would know your radius is 2. If you're told your radius, that's fine. There's one step less you have to do. You don't divide by 2. Now that we have that information, let's plug it into our formula. Remember that the radius is both A and B here. We don't know C, which is the distance between the bolts as we go around the wheel hub. That's what we're solving for. So we have all of our givens that we need on the right-hand side. A and B are both going to be 2 inches in this case, if that's what we've declared. It could have been cubits. So we're just plugging in these values. Being that I have chosen something nice with 2's in it, this calculation comes out fairly well, and a lot of you will be able to do this in your head. To get C by itself, we're going to just take the square root of both sides. So you're taking the square root of all of that to get C by itself. And that's another common mistake that I see when students are learning this. They do this calculation on the right, and then they declare that as C, because they've forgotten that this equation is set equal to C squared. So we have to take the square root to actually know the value C, so the distance between these 2 bolts in this situation. I stopped in the process right here to show you where a common mistake would be made. Students may see this 8 minus 8 as they simplify across here and think they can just write 0 here. At that point, they might make the logical decision, I can't have my solution be 0, so we'll just ignore that altogether and just do the square root of cosine of 72 degrees and get some answer there. Again, that would be wrong. We have to do this product first, 8 times the cosine of 72 degrees, and then subtract that from 8. Then take the square root of that, and we get that we have approximately 2.351141. This goes on a bit. Because of the nature of what we're doing here, these tend to be irrational numbers, and in the real world, we're working with wood, metal, things like that. That's, at some point, there's an industry standard of where you have to round to. I gave myself 6 decimal places here. A lot of shops, when you're dealing with automobiles in conventional measurements, you can measure out to the 30 seconds. If you're being really precise, you measure out to the 64ths. Let's just say we're doing to 30 seconds. So we have to take this decimal part here and turn it into 30 seconds of an inch. To do that, you take the decimal portion here, the 351141, you multiply it by 32, and then you divide by, in this case, 1,000,000. And that is simply 1 followed by as many zeros as you have digits here. So there's 6 digits here, so we divide by 1 followed by 6 digits, and that is just an algorithm for giving you 30 seconds of an inch. So this comes out to be approximately 2 and 11/32 of an inch. If you divide that out, that is just shy of this, but if you go to 12/32, you end up with 2.37. So this falls just in between the actual value and the next 30 seconds. Again, in real world mechanics, you have to have a point where you round and you have to understand what those values are. And then your entire system has to follow the same conventions so that your machines work as anticipated. So we have a distance between our bolts of approximately 2 and 11/32 of an inch. And I'm labeling this as inch here now because we started out with our given was 2 inches between the hub center and the bolt. If we had been given that this was 2 decimeters, then our solution would have been in decimeters. One thing to mention why the table in the book that the woodworker is using says you can just multiply values by a new diameter is because they chose to use a unit measure. Again, doesn't matter what that unit measure is, as long as you're scaling by the same unit. The properties of this triangle are defined in such a way that if you scale up the diameter, you are scaling up the radius by that same amount, and when the radius scales up, the chord scales up. The central angle does not change, and these angles out here, which are the base angles of the isosceles triangle, are not going to change either. So we've met the definition of a similar polygon, and that's really the heart of how trigonometry works so well, is it's based on the definition of similar triangles. So all the sides are scalable so long as you scale them by the same scalar. So once you have a value, you can multiply or divide by that value to get new lengths, because these are just the sides of a similar triangle. Let's look at the little program that I wrote now. As we begin to look at this code, you see at the top there's a shebang there. I'm on a Linux system, so that is my direction, and the code was written in respect to that idea. Going down to lines 9 through 13, these types of color codes aren't necessarily going to work quite as well on a Windows system, and you would have to call in, I believe the library is Colorama, to get the coloring more properly on your Windows system. The libraries that I'm pulling in here is NumPy, which is my expectation for doing the calculations. I pull in OS because I want to have the ability to control the display to terminal. And then I have this W Easy Print. I've had AI suggest this a couple of times to me, and the previous time that AI suggested it to me, I didn't really want to mess with setting up a new environment and dealing with that. This time, I listened to the suggestion by AI. I knew I wanted to have a PDF output. My normal mentality for having PDF output is to do LaTeX, and according to Google's AI, I could have done some Python code that gives me some LaTeX, and I've done some Python LaTeX interaction in the past, but it just seemed like the WEasy Print was going to give me a quicker, better output for the effort. So once we get past these initial couple of functions that does our heavy lifting for the calculations, you're going to see there's some CSS and HTML. I'm okay with Python. I'm not the greatest programmer probably for anything. LaTeX my best
computer language. But the AI definitely helps me with setting up CSS and HTML. I've done a very little HTML, and CSS is essentially a fairly new thing to me. I just found out the other day that when you do a comment in the CSS section, it has to be commented like you're writing C instead of like you're writing HTML. The chord calculation we see in this first function that's defined here called chord, where it pulls in the diameter and the number of sectors that you want. And then the function below that is going to build the chart in HTML and PDF. And it takes in the diameter, both diameter and number of sectors that you want are going to be input from the user. As we move on, you see the CSS there, and then we get into some of the beginnings of the HTML setup, and then we get a little more Python here that is going to do this for loop, which pulls in information from the functions to build into the table, which is going to be the output table that shows for the users, if you have this many sectors that you need, what your chord length is going to be, just like we see in the woodworking book. And then we see some of these save process functions here where it creates the HTML and the PDF outputs. And then below that you see the execution block. You get my greeting in there. So let's look at what this looks like when we start it up. So this is a terminal window. It clears the screen, and then it puts the app information at the top there, and then asks from the user what diameter that you want to use. And we'll just tell it 42 for fun. And then it's going to ask you how many sectors you want for that circle, and we'll tell it 5. And then it's going to give me feedback here, and this is the first function that I have going on here. It's going to tell us the circle's radius, so it's just taking that number and dividing by 2. It's going to tell us what the central angle is. It takes the number of sectors that we wanted and it divides 360. And then it's going to tell us the chord length. So this isn't giving us a table at all. It's just an interactive feature that just tells us the values. Then it asks us if we would like to create a chart for this specific diameter circle. And if we say yes, then that's when it's going to build that HTML and PDF so that it gives us a nice visual output where we could print it out and hang it in the shop or put it in a reference book or whatever we want to do with it. And that's where it becomes more like what we saw in the woodshop video. And then it exits its functionality and goes back to my environment prompt in my terminal. This is the HTML output that we have here, and I like green, so the AI suggestion for coloring this was in like shades of blue, and I went in and edited that code so that I got these nice green colorations in here. And then I added titles. I added my channel title up there and made sure my tab was titled, and I put the little kind of instructions on scaling in there because I do know enough about HTML to do some of that, and I figured out kind of what I didn't know about the CSS to get this to work, because the CSS had to be set up right for this library that the AI suggested I use to work to build the PDF off of the HTML. And that was the trade-off on making this work faster and not using LaTeX. It's this library that the AI suggested, we'll just take that CSS HTML code and then build the PDF off of that without the LaTeX. So we see the PDF output here is very similar to the HTML, and we have this nice document that we could print out. And then I limited how much output it had so that it came out on nice 2 pages and cut cleanly there. I can edit the code and get some more results if I need it. We can do this now in just seconds and have these done in fun types. It has floating point that's allowable. I did one for like 3.1 and such, some pi-ic number. But we can do any fun diameter that we want. And then they can be like novelty things that you could give out to your friends.